Okay, so you know how we always talk about the early universe, right?
Yeah.
We always picture this sort of like, simple,
Kind of a blank slate.
yeah, blank slate.
Right. Everything's just kind of starting to come together.
And everything's basic, right? Just like hydrogen, helium.
Exactly, yeah. Just those light elements.
It's the absolute fundamentals.
In the Big Bang.
But you know what? There are these brand new findings that are seriously shaking things up. We're
wow.
talking like flipping the script on everything we thought we knew about the universe's baby pictures. So get this. We are diving deep into the most distant galaxy ever observed.
Right.
Ever.
Oh, wow. Okay.
Jade's GSZ140.
Jade's GSZ140.
That's its name. And
That's catchy.
it's mind-blowingly far away. 13.4 billion light years.
13.4 billion light years.
Meaning we're seeing it as it was just 300 million years after the Big Bang.
So this is really early.
Super early.
Yeah.
Like 2% of the universe's current age. Just a baby universe.
Okay.
Now hold on to your hats because here comes the truly wild part.
I'm ready.
Oxygen. Oxygen
In this galaxy.
in this galaxy. Detected by none other than ALMA and the James Webb Space Telescope.
Ah, the heavy hitters.
The dream team of cosmic observation. And it's not just a fluke observation, okay? Multiple teams, multiple instruments, all pointing to the same conclusion. So today we're going to break this all down for you. Why is finding oxygen so ridiculously early a total game changer? What does it tell us about the universe's first moments? And trust me, the implications are huge. Like rewriting the textbook's huge.
Well, I'm intrigued. Let's start with the oxygen itself. Why is finding it in a galaxy this early so shocking? I mean, it's oxygen. It's everywhere.
Right. We kind of take it for granted, don't we?
Right. It's like the air we breathe.
But here's the thing. Oxygen, unlike hydrogen and helium, doesn't just pop into existence with the Big Bang.
Okay.
It needs stars. It needs stars to be born, live their lives, and then go out with a bang.
Supernovae.
Supernovae. These massive explosions that scatter heavier elements like oxygen out into space. It's a process called chemical enrichment, and it was always thought to take, well, considerable amount of time.
Right.
But this discovery blows that whole timeline wide open.
Okay, so we've got this super early galaxy
Super
with oxygen just hanging out.
just casually existing 300 million years after the Big Bang. It means those first stars as cosmic factories were working overtime. They were churning out these heavier elements way faster than we ever imagined.
It doesn't really fit with the traditional timeline, does it?
It's like showing up for a kindergarten play and finding a bunch of teenagers on stage. Sander Shows at Leiden Observatory said it perfectly. It's like finding an adolescent where you would only expect babies.
I love that. It really captures the unexpected maturity of this early galaxy. And it's amazing that we can even detect this oxygen from such a mind-boggling distance.
Oh, absolutely. That's where the power of our telescopes comes in. ALMA, the Atacama Large Millimeter Submillimeter Array, was crucial here. It can detect these incredibly faint signals emitted by oxygen in the millimeter and submillimeter wavelengths.
It's like a cosmic detective sifting through the faintest whispers of light.
Exactly. But then we need to confirm the distance and get the full picture right. Enter the James Webb Space Telescope JWST. Not only did it confirm JG's GS and C14-0's incredible distance, it gave us this stunning infrared imaging.
And spectroscopy, right? That's what really gives us the detailed chemical breakdown.
Exactly. So tell us about that. What exactly is spectroscopy, and what kind of secrets does it reveal about a galaxy?
Okay, so think of it like this. You know how a prism splits sunlight into a rainbow?
Yeah.
Spectroscopy does something similar with light from a galaxy. It breaks it down into its different wavelengths, revealing its chemical fingerprint. Essentially, it tells us what elements are present and in what quantities.
So it's like taking a blood test, but for a galaxy.
Exactly. And in this case, JWST's spectroscopy confirmed ALMA's detection of oxygen and provided a broader view of the galaxy's chemical composition. And this was all part of the JD's program, a dedicated effort to study these earliest galaxies.
So it's like a double whammy of confirmation. ALMA pinpoints the oxygen, and JWST gives us the panoramic view.
Precisely. And the fact that this dual confirmation comes from these incredibly sophisticated instruments means this oxygen detection is super reliable. We're not basing this on some shaky data point. This is solid.
Okay, so we've got this shockingly evolved galaxy flaunting its oxygen way earlier than expected.
Right.
So where does that leave our current understanding of the early universe?
Not in a good place, to be honest. This throws a serious wrench into our established models of galaxy formation and evolution. We always thought that the first galaxies would be these simple structures dominated by those light elements from the Big Bang, hydrogen and helium.
Primordial soup.
Exactly. But this abundance of oxygen suggests a much more rapid and complex process.
So are we saying that our understanding of the very first stars, those population 3 stars, is flawed?
It's looking that way. Maybe they were much more massive and had shorter, more dramatic lifespans.
Leading to faster supernova explosions.
Exactly. And a much faster dispersal of heavier elements throughout the early universe. It raises a fundamental question. What kind of stars could have lived and died so quickly to produce this oxygen in such a short cosmic time frame?
It's like the universe hit the fast-forward button on star formation and evolution.
Exactly. And this early chemical enrichment, as you said, likely has implications for another pivotal era in cosmic history, cosmic reionization. Now, this is when the universe transitioned from opaque to transparent.
Ah, yes. The universe's let there be light moment.
Exactly. Early on, the universe was filled with neutral hydrogen, which blocked light. But then the radiation from the first stars and galaxies started ionizing this hydrogen, making the universe transparent.
And could Jade's GS Z14-0, with all its brightness and unexpected maturity, have played a role in this cosmic light show?
Absolutely. Its early abundance of heavier elements might have influenced the types of stars it hosted and the amount of high-energy ultraviolet radiation they emitted.
Which is key for ionizing that neutral hydrogen.
Precisely. It suggests that the early universe was far more dynamic and active than we previously thought.
It's like the universe didn't just slowly ease into things. It burst onto the scene ready to go. Now it's important to remember that this discovery is happening in a year jam-packed with exciting space science news. The Euclid mission released its first data, giving us these amazing wide-field views of the cosmos.
We're even seeing auroras on Neptune now.
Auroras on Neptune, who would have thought? Plus, missions like SpaceX's Fram-2 and NASA's Lucy spacecraft are pushing the boundaries of exploration. We've even got hints of hidden galaxies out there and new data from the Dark Energy Spectroscopic Instrument, or DSI, suggesting a subtle shift in the influence of dark energy.
It's an amazing time to be following space science, that's for sure. So many exciting discoveries. But this oxygen detection in Jade's GS Z14-0, it feels different.
It does, doesn't it? And I think it's because those other discoveries are incredible in their own right, but they're kind of adding details to the picture we already have.
Right.
This oxygen detection, it's redrawing the picture entirely. It's forcing us to rethink the very foundations of our understanding of how the universe evolved in its earliest stages.
It's a fundamental shift in our understanding of the universe's origins.
And it's all thanks to these incredible advancements in technology. JWST's ability to see in the infrared spectrum, that's game-changing.
It is.
Because light from these incredibly distant early galaxies, it gets stretched out as the universe expands, shifting it into the infrared. Older telescopes like Hubble couldn't see this light effectively.
Right.
But JWST, it can cut through that cosmic fog and capture the faintest glimmers from these primordial galaxies.
It's like having a time machine peering back to the universe's earliest moments.
And of course, we can't forget ALMA working in tandem with JWST. It's this perfect partnership. JWST gives us the big picture, the images, the overall spectrum. And ALMA zooms in, pinpointing specific elements like our oxygen.
Together, they're giving us this incredibly detailed and comprehensive view of the early universe. It's a testament to human ingenuity and our drive to understand the cosmos.
So to sum it all up, the early universe was a much more lively and chemically mature place than we ever imagined. This discovery of oxygen in JD's GS Z14-0, it's proof that galaxy formation and the creation of heavier elements happened much, much faster than our models predicted.
It's like the universe decided to skip the slow warm-up and jump straight into the action.
Exactly. And the most mind-blowing part is that this is just the beginning.
Oh, yeah.
If galaxies like JD's GS Z14-0 were already this developed so early in the universe's history, what other surprises are lurking out there? What other secrets are waiting to be uncovered as our telescopes get even more powerful? It really makes you wonder if our current picture of the early universe is just the tip of the iceberg.
You know, as we continue to explore and refine our understanding of the cosmos, one thing's for sure, the universe is full of surprises. And that's what makes studying it so endlessly fascinating.
Absolutely. And on that note, I think it's time for us to wrap up this deep dive.
Yeah, I think we've given everyone a lot to think about.
Definitely. Thanks for joining us on this cosmic adventure. Until next time, keep looking up and keep those questions coming, because